In this video, we're going to go over some practice problems from chapters 3 and 4 of our textbook. Now, in chapter 3, we're looking at solving systems of linear equations. So, with section 3.1 here, let's look at this first question. We want to determine whether this given ordered pair is a solution of this given system. So, in order for this to be a solution, this guy needs to satisfy both of these equations. So, we'll go ahead and plug in these values for x and y into this first equation here. We want to make sure that we get a true statement. Now we're going to have 10 minus 2 on the left-hand side. So we're going to get that 8 is equal to 8, which is a true statement. So that means this guy is going to be a solution to this equation here. But in order for it to be a solution to the entire system, it needs to satisfy both of these equations. So let's plug in these values into the second equation as well. We're going to have 3 times 5 plus 2 times 2 is equal to 20. So this is going to give us 15 plus 4. And in this case, we're going to get that 19 equals 20, which is not a true statement. This is false. So this tells us that this given ordered pair is not going to be a solution to this system because it doesn't satisfy both of these equations here. So we'll go ahead and write that. We'll say that 5 comma 2 is not a solution. All right. Now for this next one, we want to solve this system by graphing. So we have this system of our two linear equations here, and we know that in order to solve a system by graphing, we're going to graph both of these equations, and the point of intersection, if there is one, will be our solution to the system. So we're going to go ahead and graph both of these guys. Now, looking at this first equation here, we have x plus y is equal to 4. Now, we know that we can graph this by maybe creating a table, plugging in different values for x, and see what we get for y. Or we can write this in our slope-intercept form. When it's in this form, we'll know exactly what our intercept is and what our slope is, making it easier to graph. So let's go ahead and do that. We're going to do x plus y is equal to 4. Now, slope-intercept form is y is equal to mx plus b. So what we need to do is isolate y. In order to do that, we're going to subtract x on both sides of this equation. We're going to end up with y is equal to minus x plus 4. Now, the reason why I wrote this minus x first is so it would be exactly in this form. Now we can see exactly what our slope and our y-intercept is. Our slope is going to be the coefficient of our x value, so it's going to be -1. And then our y-intercept is going to be 0, comma this value, which we call b. So our y-intercept is 0, comma 4. So with this, we can graph this equation, and let's do some color coding here. This is the line that we're wanting to graph, so let's do it in blue. The first thing we're going to do is plot this y-intercept and then find some more points on this line using our slope. So since our slope is -1, we're going to go up 1 and then to the left 1, up 1 to the left 1 in this direction. And in the other direction, we're going to go down 1 to account for that negative and to the right 1. So our line is going to look like this here. All right. Now let's do the same thing for this second equation here. We have 2x minus y is equal to 2. Let's again get it in slope-intercept form. We're going to subtract by 2x on both sides of this equation. So we'll get minus y is equal to minus 2x plus 2. But y is not completely alone here. We need to completely isolate it. Right now we have a -1 in front of it. So we're going to divide both sides by -1. And then we'll get y completely alone on the left-hand side. Then on the right-hand side here, we have minus 2x divided by -1. So that's going to change the sign of this and make it a positive 2x. And then for our second term, we have 2 divided by -1. So that'll give us a -2. So dividing by -1 on both sides of our equation just changes the sign of both sides of our equation. All right, so our slope in this case is going to be 2 and our b value is -2. So our y-intercept is going to be 0, comma -2. So let's go ahead and plot this. We're going to do this guy in green here. The first thing we're going to do again is find our y-intercept, which is going to be right here. And then we're going to find other points on this line using our slope. Our slope is +2, so we're going to go up 2 to the right 1, up 2 to the right 1. We'll repeat this process there. And in the other direction, we're going to go down 2 to the left 1. All right, so this is our line here. Now remember, the point of intersection is going to be the solution. So the point of intersection between these two lines here is given by 2 comma 2. So we'll say our solution set in set notation is going to be the ordered pair 2 comma 2. All right, so for the next two examples, we want to solve both of these algebraically, and there's two different methods for doing so. The first method is substitution, and the second one is elimination. So for question 37 here, or 31 here, let's solve the system using substitution. Now, in order to do that, we want to get one of these variables completely alone from either one of these equations. But notice, let's look at this bottom equation here. If I wanted to isolate x, eventually I would have to divide both sides of our equation by 2, and that might make this guy a little more complicated. Similarly, if I wanted to solve for y, I would have to eventually divide both sides of the equation by 5, again, making this more complicated with fractions. Similarly, for this top equation, if I wanted to solve for x, I would eventually have to divide by 3. So to make our lives a little bit easier, if I want to isolate one of these variables, the wisest choice would be this guy here, because the coefficient in front of this variable y is just going to be -1. So all we'll have to do is divide by a -1 in the end, which we know just changes the sign of both sides of our equation. So let's try to isolate this guy. So we have our equation 3x minus y is equal to 10. We want to completely isolate y. So the first thing that we're going to do is we're going to subtract 3x on both sides of our equation. We're going to end up with minus y is equal to minus 3x plus 10. And like I said, in the end, we're going to have to divide by -1 to get y completely alone, which we know is just going to change the sign of both sides of our equation. So now we have one of our variables completely isolated, and using the substitution method, we're going to take this y value and substitute it directly into our other equation. So we're going to substitute 3x minus 10 into this y here. So we're going to have 2x plus 5y is equal to 1, which is going to turn into 2x plus 5 times 3x minus 10 is equal to 1. Now, by doing this, we now have an equation that's in terms of just one variable x instead of two different variables. Since we have an equation in terms of just one variable, we can easily solve for this guy. So the first thing that we're going to do is distribute this 5 here. We're going to have 2x plus 15x minus 50 gives us 1. And in the same step, I'm going to combine these guys. These guys are like terms, and I'm going to add 50 to both sides of this equation. Because remember, we're trying to isolate x. So this is going to give us 17x is equal to 51. And then lastly, to get x completely alone, we'll divide both sides by 17 to give us 3. So by solving for y in the very beginning here, we got this equation, and then we substituted it directly into this y variable with our other equation and solved for our remaining variable x. Now with this value of x, we can plug this into this equation. So y is going to be equal to 3 times 3 minus 10. So this tells us y is equal to -1. So the solution set for this example is going to be 3 comma -1. All right, so that's how we would solve the system using substitution. Now let's look at solving a similar system using elimination. Now in this case with elimination, the whole idea is to be able to add our two equations together, and one of the variables will be eliminated. Now notice if we were to add both of these equations together, we would end up with minus 6x here and 4y here. So doing that addition process actually doesn't eliminate either one of these variables. So what we need to do is we need to manipulate one or both of these equations so that we can get rid of one variable when we add them together. So for example, in this case, let's say I wanted to eliminate y. What I want to do is be able to add these guys together and the y goes away. So since I have a positive 3y in this case, what I might want to do is change the coefficient of this y to a -3. When I do that, I'm going to get plus 3y minus 3y, and these guys would cancel. Now, in order to make this coefficient a -3, what I would have to do is multiply this guy by a -3. But whatever I do to one side of the equation, I have to do to the other in order to make sure the equation remains unchanged. So we're not actually changing the solution set for this equation, we're just changing its form. So what I mean is, let's multiply both sides of this equation by -3. Doing that, we're going to get a new system here. We still have this first equation. And remember, our second equation's solution set is the same. We're just changing its form. So this is going to become, we're going to have 12x because we have -3 times -4x. Then we're going to have -3 times y. So this is going to give me -3y. And then on the right-hand side, we're going to have a +9. So now notice, if I were to add these guys together, I'm going to end up with 10x because we have -2x plus 12x. And then here I have 3y minus 3y. And just like we said in the beginning of this problem, these guys are going to cancel and we've successfully eliminated our variable y. Now, on the right-hand side of this equation, we're going to have 1 plus 9, which gives us 10. And now we can easily solve for our variable x. We'll divide both sides of this equation by 10. This is going to give us 1. And now we have our value for x, and we can find our value for y by plugging this x into either one of our original equations. Let's use our first equation here. We have -2x plus 3y is equal to 1. I'm going to plug this value for x into this equation here to solve for y. So I'm going to have -2 times 1 plus 3y is equal to 1. So this is going to give me a -2 plus 3y is equal to 1. And then I will add 2 on both sides of this equation. This will give me 3y is equal to 3. So dividing both sides by 3, we're going to get that y is also equal to 1. So our solution set in this case is going to be the ordered pair 1, comma 1. So that's how we would solve this system using our elimination method. All right, so this brings us to section 3.3, where we're going to be looking at applications of systems of linear equations. So we're going to be given some word problems, and essentially we're going to take the information in these problems and create our own systems of linear equations and solve them. So let's look at question 22 here. We're told at a business meeting at a coffee shop, the bill for 2 cappuccinos and 3 cafe lattes was 1975. And at another table, the bill for 1 cappuccino and 2 cafe lattes was 11.97. So what we want to figure out is how much each type of beverage cost. So our two unknown quantities are the price of each of these beverages. So let's set up variables for these unknown values. Let's let our variable C be equal to the price of our cappuccino. And then we'll let our variable L be the price of our cafe latte. Okay, so these are our two unknown quantities. And we want to set up a system of linear equations and solve it for these quantities. And we're going to be able to set up the system using the information in this problem. So let's do some color coding. We're told that the bill for 2 cappuccinos and 3 cafe lattes was 1975. So in blue here, that's going to look like 2 cappuccinos plus 3 cafe lattes is equal to $19.75. Then our second piece of information here tells us that the bill for 1 cappuccino and 2 cafe lattes was 11.97. So that's going to look like 1 cappuccino and 2 cafe lattes totals $11.97. So this is going to be our system of linear equations. Now, we can use either method to solve this system here. We could, for example, isolate this variable C and then plug that value for C into this equation and get our value for L. For this particular example, I'm going to use the method of elimination, however. So if I want to, let's say, eliminate this variable C, what I would do is I'd multiply both sides of this equation by -2 so that this and that -2C will cancel. So let's multiply both sides of this equation here by -2. Doing so, we're still going to have this equation here, but our second equation is going to become -2c minus 4L is equal to negative 23.94. Now, if we use our method of elimination, we are going to add these guys together, and our variable c is going to be eliminated. 2c minus 2c is just going to give us 0c. So we're left with 3L minus 4L. This is going to give us a negative L. And then we're going to have 1975 minus 2394. This is going to give us a negative 419. But this says negative L is equal to this. So in order to get L completely alone, we're going to have to divide both sides by -1, changing the signs of both sides of this equation. So we're going to get that a cafe latte costs $4.19. Now, with this information, we can then find our other unknown value, the cost of the cappuccino here. So we'll take this L and we can plug it into either one of these equations here, because remember our solution needs to satisfy both equations in our system in order for it to be a solution. So we could plug this L into either one of these guys. I'm going to choose to plug it into this second equation here. So we have C plus 2L, to make this nicer, 2L. It's going to give us the 1197. So we'll plug L directly into this equation here. We're going to multiply 2 by the 419. This is going to give us 838. And then lastly, we'll subtract that amount from both sides of our equation. So we'll have 1197 minus 838. This is going to give us 359. So this tells us that each of the cappuccinos, or each cappuccino costs $3.59, and each latte costs $4.19. So those would be our final answers. All right, so for this next example, we're told that a scooter travels 20 miles in the same time that a bicycle travels 8 miles. If the rate of the scooter is 5 miles per hour more than twice the rate of the bicycle, find both rates. So we have two unknown values that we're trying to find, and that's going to be the rates of both of these methods of transportation. So we have our scooter and our bike. These are our two methods of transportation. Let's let x be equal to the rate of the scooter and y be equal to the rate of the bike. We're trying to find both of these values. We're also given that the distance that the scooter traveled is 20 miles and the distance that the bike traveled was 8 miles. Now we don't know the time for either of these guys, but we do know that it took the same time to travel these distances. So we're going to use our equation. Distance is equal to rate times time in this case. Now we have our distance and we have these variables for our rate. These are the quantities that we're trying to find. And we don't necessarily have a time, but we know that the times are equal. So what we're going to do is we're going to solve for time. Let's divide both sides of this equation by r. We're going to get that time is equal to distance over our rate. So with this information, let's write an equation for both of these guys in terms of time. Meaning, for our scooter, the time traveled is going to be the distance traveled, which was 20 miles, divided by the rate of the scooter. And then for our bicycle, the time traveled is going to be this distance divided by this rate. Now, remember how we were told that the scooter travels 20 miles in the same time that this bicycle travels 8? This means these times are going to be equal to each other. It took the same time for it to travel this distance and for the bike to travel this distance. So what we can do then is we can set these two times equal to each other. So we have 20 divided by x is equal to 8 divided by y. Now, we can work with this equation. However, these fractions here make this a little tricky. Instead, what we can do is we can cross multiply to simplify this. If we cross multiply, we're going to end up with 20 times y is equal to 8 times x. Now, this equation becomes much easier to work with. All right, so this is our first equation. And let's go ahead and write this over here where we have more room. Now, usually we like to write our equations in standard form. So what I'm going to do is I'm going to move this 8x over to the other side. So minus 8x minus 8x. I'm going to have minus 8x plus 20y is equal to 0. So this is our first equation. Now, we were given another piece of information here. We were told that the rate of the scooter is 5 miles per hour more than twice the rate of the bicycle. So remember, the rate of our scooter was x, and we're told that this is equal to 5 miles per hour more than twice the rate of the bicycle. And we know that the rate of the bicycle was y. So this can be written as 2y plus 5. So this equation comes from this information here. So now we have this system of linear equations, and we want to figure out what x and y are. These are going to be the rates of our two methods of transportation. So what we'll do in this case is we'll take this value for x and we'll just plug it directly into this equation. I'm not using elimination in this method. Or in this example, we're going to be using the substitution method. And the reason being is because we already have an equation or we already have one variable that's completely isolated. So we can take this equation and plug it directly into here. So doing that, we're going to have minus 8 times x, which is 2y plus 5 plus 20y is equal to 0. All right. So let's solve for our variable y. The first thing we're going to do is distribute this negative 8 to both terms in our parentheses. This is going to give us negative 16y. Let's scroll down. This will be negative 16y, and then we're going to have negative 8 times 5. So this is going to give us a negative 40 plus 20y is equal to 0. So we have some like terms here. We have this minus 16y, this 20y, so we'll combine those. And in the same step, I'm going to add 40 to both sides of this equation. Doing so, we're going to end up with minus 16y plus 20y, so that'll give me 4y on the left-hand side. And then on the right-hand side, it's going to give us that 40. And lastly, to get y completely alone, we'll divide both sides by 4. So this tells us that the rate of our bike in this case is going to be 10 miles per hour. And then lastly, if we want to find the rate of our scooter, we're just going to plug in this value for y directly into this equation because we already have our x variable isolated here. So our x, or the rate of our scooter, is going to be twice the rate of the bicycle plus 5. So that's going to be twice the rate of our bicycle plus 5, which is going to be 25 miles per hour. All right, so for the last problem in section 3.3, we're going to be dealing with the system of 3 linear equations and 3 unknown variables that we're trying to find. So we're told that the perimeter of a triangle is 70 centimeters. The longest side is 4 centimeters less than the sum of the other two sides, and twice the shortest side is 9 centimeters less than the longest side. With this information, we want to find the length of each side of this triangle. So the first thing that we're going to do is we'll draw a diagram here to visualize what's happening. Let's let x be equal to our shortest side, y be equal to the middle, and z be equal to our longest side. So these are all of our unknown values that we're trying to find. And then z is our longest side. All right. So with this information, let's create our system of equations. Our first equation could be given by this. We're told that the perimeter of a triangle is 70 centimeters. And we know to find the perimeter of a triangle, we're just going to add the length of all 3 sides. So this is going to be x plus y plus z is equal to that perimeter of 70 centimeters. All right, then we're told that the longest side is 4 centimeters less than the sum of the other two sides. So the longest side is given by z, and this is going to be 4 centimeters less than the sum of the other two. So we're going to take the sum of the other two sides, and it's going to be 4 centimeters less than that. So we're going to subtract out 4. And then our last piece of information, remember, if we have 3 unknown values, then we need to have 3 equations to find them. And the last piece is that twice the shortest side is 9 centimeters less than the longest side. So twice the shortest side is going to be 2 times x. And this is going to be 9 centimeters less than the longest side. So it's going to be the longest side of z minus 9. So we have our three equations here. Now what we're going to do is we're going to write these in standard form. Let's see if we can easily use elimination in this case. So our first variable, or sorry, our first equation is already in standard form here. Now for our second equation, to write this in standard form, all of our variable terms need to be on one side and our constant term on the other. So what we'll do in this case is I'm going to add, or I'm going to subtract z to both sides of this equation and add 4 to both sides. So if I were to subtract z, I'm going to get x plus y minus z. And then since I'm adding 4 to both sides, I'm going to get a positive 4 on the other side. And then lastly, for this one here, I'm just going to subtract z to this side. I'm going to get my variable terms 2x minus z, and then my constant term of minus 9 separated. All right, so this is going to be our system in our standard form. And just as a little refresher, standard form, I guess we can write it over here, is ax plus by is equal to c. This is going to be standard form of our equation. So all of our variable terms are on one side and then our constants on the other. Okay, so from here, we have an extra step. We have three equations and three unknown values. And what we want to do when we're solving this type of system of equations is we want to find the equation that has one of the variables missing. So notice our first two equations have all three variables, but this one is missing y. So for our first step here in solving this, we need to identify the equation that is the simplest or has one less variable. So in this case, y is missing. So the first step in order to solve this system, so step one, is we're going to get another equation without y. So we're going to get another equation without y. And the reason being is if we find another equation without y, then we can take that equation and this one, and we'll end up with this system of two linear equations and two unknowns, which we know exactly how to solve for, as we've seen in the last several examples. So what we're going to do is we're going to use these two equations here to eliminate y and get another equation. So we'll use these to eliminate y. All right, so in order to do that, if we wanted to eliminate y here, if we were to add both of these equations together, we would get 2x plus 2y, and z would be eliminated, but that's not what we're trying to do. We're trying to eliminate y. So in order to do that, I'm going to multiply this equation by a -1 so that our y's will cancel. So if I were to multiply both sides of this equation by -1, I'm going to end up with, and let's write it under our first step here. We're going to have x plus y plus z is equal to 70. This is our first equation. It's unchanged. But our second equation is going to become minus x minus y plus z is equal to -4. So this is what we get when we multiply both sides of this equation by a -1. And we're doing this so that when we add these equations together, our variable of y will cancel. We have a plus y and a minus y, so these guys clearly cancel. And in that same step, what happened was our x's also canceled, which is nice. This leaves us with just a 2z on the left-hand side. So we're going to have 2z, and then on the right-hand side, we're going to have 66. So we can automatically solve for z by dividing both sides by 2. Okay, so now our second step is we're going to plug in this known value if possible. So we'll plug in the value that we found. So doing so, we could plug z directly into this equation here. We would have, so we have our equation of 2x minus v is equal to -9. So we'll plug in our value for z directly into this equation and then solve for x. So we'll add 33 to both sides of this equation. We're going to get 2x is equal to 24. So this means x is going to be equal to 12. So now we found both values. We found our shortest and our longest side of this triangle. So now, since we have these two values, we can easily plug them into any one of these equations with y and solve for y. So let's plug this value for x and z into this top equation here. So we have x plus y plus z is equal to 70. And we're going to plug in our known values. So 12 plus y plus 33 is going to give us 70. So y plus 45 is equal to 70. So this tells us that y is equal to 25. And in this case, in this step two, we're actually plugging in our found values. So we found x and z. So just to recap for this one, we have three unknown values, so we need three equations to find them. We took these equations from the problem and translated them into standard form, just so that we could easily see what's going on with all of our like terms. Now we notice that our variable y is missing, so that is nice. This is going to be a simplified or an easier equation to work with. So this gives us a direction to move in. If y is missing in this case, let's take the remaining two equations and see if we can eliminate y from these guys as well. Doing that, we ended up eliminating our variable x as well. But if we hadn't eliminated x, we would have ended up with an equation in terms of x and just z, which we could then use with this equation to solve for 1. But in this case, it was nice that x canceled out as well, so we were able to solve for z. Took that z value, plugged it into this equation, got our x value, and then lastly, we plugged in both of these values into this equation to get y. So a lot of steps going on here, but following this process, we were able to find all sides of this triangle. Now, in this next section, we are working with integer exponents. So what we're wanting to do is simplify exponential expressions or equations, and we're going to do so using these rules here. So this is a nice summary of definitions and rules for exponents, and this can be found in our textbook. This is just a screenshot directly from our textbook. So we're going to use each of these rules here to answer the following questions. So for section 4.1, we have these exercises here, and for each one, we want to simplify each expression and make sure our final answer has only positive exponents. So let's look at this first one here. We have the product of these three exponential expressions. So this tells me we might be using our product rule since we have the product of these guys and they all have the same base of a. So going back up to this summary here, our product rule says that if we're taking the product of two exponential expressions that have the same base, then in order to simplify this, we're going to take that base and raise it to the sum of these exponents, this n plus n. So we're going to do the same thing here. In order to simplify this, we're going to take our base of a and raise it to the sum of these exponents. So our a raised to the negative third times a squared, just rewriting this expression. This is going to be the same thing as our base a raised to negative 3 plus 2 minus 4. So we're just taking the sum of all of these exponents. This is going to give us a raised to the negative fifth power. But remember, we want to make sure our final answer has only positive exponents, so we need to rewrite this with only positive exponents. Now, in order to do so, let's go back up to this summary here. These are our special rules for negative exponents. So this is from our textbook, and I also wrote this one in here. If we have something raised to the negative nth power, rewriting this with a positive exponent is the same as taking the reciprocal of this. And then in our denominator here, we're going to have our positive exponent. So the reciprocal of a is going to be 1 over a raised to this positive power. Now we also have this case here where we already have this fraction with our negative exponent. And again, to write this as a positive exponent, we're just going to take the reciprocal of this and raise it to that positive power. So the reciprocal of 1 over a is just a. So in our example, we have a raised to the negative fifth power. So to rewrite that with a positive exponent, it would be 1 over a to that positive fifth power. So this is going to be 1 over a raised to the positive 5. So that would be our final answer since it's fully simplified and we have positive exponents. All right, let's look at this next example. We have 4 raised to the negative fourth power, and this entire thing is being raised to the negative second power. So in this case, we're going to be using our power rule. And we have a couple different versions of this. As you can see here, our power rules are here. Now, the case that we're looking at, we have something raised to a power enclosed in parentheses, and it's being raised to a different power. So in this case, what we're going to do is we're going to take this base and raise it to the power of the product of these two exponents. And don't confuse this with the product rule. In this case, we add these exponents with this power rule where we're taking an exponential expression raised to an exponential power. We're going to take the product of those exponents. So in this case, this is going to be the same thing as our base is going to be 4, and then we are going to take the product of our exponents. So this is going to be 4 raised to the 8th power. And we could evaluate this, just plug into our calculator 4 raised to the 8th power, or we can leave it as this. All right, let's look at 125 here. So we're going to be combining a bunch of different rules. In this first, let's look at this first power. We have 5 times a raised to the negative 1, and this entire thing is being raised to the 4th power. So let's focus on just this part for a moment. Now, again, we have an exponential expression raised to a power, so this tells me we are going to be dealing with our power rule. Now, this is slightly different from the last example, and that's because this guy inside our parentheses being raised to this power is a product. We have 5 times a to the negative first. So we have this product being raised to the 4th power. So this would be the second case of our power rules. We have the product of two things, A and B, being raised to the nth power. Now, this is going to be simplified to A raised to the nth power times B raised to the nth power. So we kind of think of this m as being distributed to both of these guys within this product. So that's what's going to happen here with this guy in blue. We're going to have that this 4 is being distributed to both terms in this product. So we're going to have 5 raised to the 4th power, and then we're going to have a raised to the negative first power being raised to the 4th. So let's keep this enclosed in parentheses. We have a raised to the negative 1 to the 4th power. So we just distributed this 4 to this 5 and to this guy here. All right, now let's look at this second power. We have a raised to the second power, and this entire thing is being raised to the 3rd power. Well, this is very similar to what we saw in the last example. What we're going to do in this case is just take the product of these exponents. So this is going to be a raised to the negative 6 power. So let's keep evaluating this. We're still going to leave this guy here. And again, we're going to use our first power rule. If we want to simplify this, this is going to be this exponent times this one. So we're going to have negative 1 times 4. And then we still have a raised to the negative 6. So let's keep simplifying. In this case, we're going to get a raised to the negative 4th power. And then we still have this a to the negative 6. Now, notice we have the product of 3 different exponential expressions, but 2 of them have the same base. We have a raised to the negative 4 and a raised to the negative 6. So we can use our product rule again, just like we saw in the first example of this section. We're going to have 5 raised to the 4th power, and then we're going to have a raised to the sum of these 2 exponential powers here. This is going to give us 5 raised to the 4th power times a raised to the negative 10th power. Now we're not done yet because remember we need our final answers to be in with positive exponents. So we're going to rewrite this using the same rule that we saw in the first example. We want to rewrite this with positive exponents. This is going to be the same thing as 1 over a raised to the 10th power. And remember this 5 raised to the 4th power is multiplying this whole thing. So in order to simplify this, kind of condense it, we're just multiplying straight across. So this is going to be 5 raised to the 4th power over a raised to the 10th power. And then this is acceptable as a final answer, or we could evaluate that 5 raised to the 4th power. This is going to be 625 divided by a raised to the 10th power. So either one of these are acceptable answers. All right, let's look at question 127 here. So we want to simplify this. Now notice we have the product of 2 different exponential expressions, z raised to the negative 4 and x cubed, and this product is being raised to the negative 2nd power. So this tells me we're going to be using our product rule, or sorry, our power rule, and it's going to be the second case here where we have the product of 2 things being raised to a power. This power is going to be essentially distributed to both things. So what we have here is we're going to have z raised to the negative 4th power raised to the negative 1 times x cubed raised to the negative 1. Now we're going to use our first power rule here that says we're going to take the product of these 2 exponents for both of these expressions. So we're going to have z raised to the -4 times -1, and then x raised to the 3 times -1. So this will give us z raised to the fourth power times x raised to the -3rd power. And then lastly, we don't want negative exponents. So we're going to have z raised to the fourth power times 1 over x cubed, which is going to be the same thing as z raised to the fourth over x cubed. So this would be our final answer. All right, so for this next problem, we're looking at the quotient of these two expressions. Now, this fraction bar can be thought of as a grouping symbol, so it's best to first simplify everything in our numerator and then our denominator, and then apply our quotient rule for exponents. So let's simplify everything in our numerator first. Notice we have the product of these three things in our exponent or in our parentheses, but we don't have it raised to any power here. So what we can do is just rewrite this as the product of these four things. We are going to have 3 times p times q squared. Now, in our denominator, we can't simplify this any further, so we're going to keep it as is. Now, notice we have q raised to the first power times q raised to the second power, so we can use our product rule. Since these guys have the same base, we can add their exponents. So we're going to have 3 times p times q raised to the 1 plus 2 over this denominator. So let's simplify this. We're going to have 3 times p times q cubed divided by this same denominator. Now from here, we can start simplifying. Notice we have a 3 in the numerator and a 6 in the denominator. So this is going to give us a coefficient of 1/2. 3 divided by 6 is the same thing as 1 divided by 2. So that's going to be out front. And then the rest of this expression is going to be simplified using our quotient rule. So let's scroll back up to this here. So our quotient rule says that if we have two exponential expressions that have the same base, what we can do to simplify them is take that base and subtract their exponents in this order. So we're going to take the exponents from the numerator and subtract the exponents from the denominator. So in this case, we have our p's here. So our base is going to be p, and we're going to take this exponent of 1 and subtract our exponent of 2. So we're going to have p raised to the 1 minus 2. Now for our q variables here, we have the base of q, and we're going to raise it to the power of 3 minus 4. So we're going to have q raised to the 3 minus 4. So simplifying this, I'm running out of room. Let's go up here. We're still going to have this 1/2 out front. Then we're going to have p raised to the negative first power, and then q raised to the negative first power. All right, so we still want to simplify this further because our final answer can't have negative exponents. So we're going to rewrite these with positive exponents. This is going to look like 1/2 times 1 over p times 1 over q. And then fully simplifying this, we can just multiply straight across. So this is going to be 1 over 2pq. So this would be our final answer. All right, so this brings us to our last problem in this section. So notice we have the quotient of these two exponential expressions, and this entire thing is being raised to the negative second power. So there's a couple different ways we could go about this. First, we could distribute this -2 to every single term in our numerator and every single term in our denominator. That would be our power rule, or one of our power rules. However, it might be easier to first simplify everything inside of our parentheses. And the reason being is because notice the numerator and the denominator are fully simplified. We can't simplify them separately any further, but we could use our quotient rule to kind of reduce this and potentially get rid of this quotient. So let's go ahead and try that. So we're still going to have this entire thing in parentheses. We're still going to have this 8 here that's not going to simplify with anything. But using our quotient rule, we're going to take this first base of x and we're going to raise it to the -6 minus fourth power. So this is our quotient rule. Then we're going to do the same thing for our second base, this y. We're going to raise it to the 3 minus -4 power. So 3 minus -4. And again, this entire thing is being raised to the negative second power, but we're going to deal with that power on the outside later. So let's simplify this. On the inside, we're going to have x raised to the negative 10th power, and then y raised to the 7th power. And it's going to be positive because we have 3 minus a negative 4. So this is going to give us a positive 7. So everything inside of our parentheses simplified to this just by using our quotient rules. So from here, what we're going to do is use our power rule and distribute this negative 2 to everything in our parentheses. So this is going to be 8 raised to the negative 2nd power. Then we're going to have x raised to the negative 10th power is being raised to the negative 2nd. And similarly, y to the 7th is being raised to the negative 2nd. So notice we have 8 raised to the negative 2nd power. Let's already write this with positive exponents. This is going to be 1 over 8 squared. Now for the second term here, we know that our power rule says that if we have an exponential expression raised to a power, we're going to take the product of these two guys. So this is going to be x raised to the negative 10 times negative 2. So this is going to give us a positive 20. And then for our y here, this is going to be y raised to the 7 times negative 2. So this is going to give us negative 14. All right, let's keep simplifying this. Notice that we have 1 over 8 squared, so that's going to be 1 over 64 for this guy. And I'm choosing to evaluate this exponent since 64 is not too big of a number. If we wanted to evaluate something like we saw in this example, 625 is fine too, but notice in this example that would be a pretty big number. So it's up to you on what you want to evaluate. In this case, I'm going to leave that as 64. Now we still have this x raised to the 20th power. We can leave that as is. It's not a negative exponent, but notice we have y raised to the negative 14, which we know is going to be written as this here. So let's simplify this. We have these fractions here, so in order to simplify this, we're just going to multiply straight across. So in the numerator, we're going to have x raised to the 20th power, and in our denominator, we're going to have 64 times y raised to the 14th power. So this would be our final answer for this one. Now, in this last section of this video, we are looking at scientific notation. So scientific notation is used to write very big or very small numbers in a condensed form. Now, that form is given by this here. We're going to have n times 10 raised to the nth power, where n is going to be a number between 1 and 10. So n needs to be between 1 and 10. And then this lowercase n here is going to be our exponential power, and it's going to be the amount of times that we move our decimal to make these really big numbers smaller or these really small numbers bigger. So let's look at a couple examples here. For 10, we want to write this number in scientific notation. So we're going to want to write this in a condensed form. And we're going to start with this decimal here. So with any number, we're always going to have a decimal on the right-hand side of it. And we're going to move this decimal however many places so that we have a number between 1 and 10. So what I mean is, let's take this decimal and move it 1, 2, 3 units. By doing that, we end up with the number 1.6, which is a value between 1 and 10. And we're going to write this as times 10 raised to the 3rd power, since we moved that decimal 3 units. Now, this value, this n here tells us how many times we're going to move the decimal, because if I were to move the decimal 1 2 times, I would end up with 16. And 16 is not a value between 1 and 10. So that's how we know to move the decimal one more time. Let's look at this example here. Now, in this case, we're dealing with a really small number. So we're going to take this decimal and we're actually going to move it in the opposite direction. So we're going to go 1, 2, 3, 4, 5 units. And we know to stop here between the 7 and the 2 because we're going to end up with the number 7.2. And this is a value between 1 and 10. If we were to stop here, we would end up with 0.7, which is not between 1 and 10. And if we were to go past this 2, we would end up with 72, which again does not satisfy this. So we have 7.2 times 10, and we moved this decimal 5 units. But since we moved this decimal 5 units to the right, and this is a really small number, this is going to be written as minus 5. So if we move the decimal to the right with a really small number, we're going to have a negative exponent. And if we move it to the left, making a bigger number smaller, we're going to have a positive exponent. So Let's look at these next two examples. In this case, we're given two numbers in scientific notation, and we want to write it in standard notation, or in other words, do the reverse order of what we did in the last two examples. So in this case, we have 1.2 times 10 to the negative 4. So this negative exponent automatically tells us we're dealing with a small number. So we're going to move this decimal to the left here. And we're going to move it to the left 4 times. So we're going to have 1, 2, 3, 4. Let's actually write this a little bit nicer here. We have 1.2, and we're moving this 1, 2, 3, 4 units to the left. So we're going to have a decimal value there, and we're going to fill in these spaces with zeros. So this guy in standard notation is 0.00012. All right, let's look at this one here. We have 8.91 times 10 to the sixth power. Now, since this exponent is positive, we know that this is actually a big number. We're going to move this decimal 6 units to the right. So we're going to go 1, 2, 3, 4, 5, 6 units to the right and fill in these spaces with zeros. So this guy written in standard notation is this here. All right, so that's how we would move from scientific to standard or from standard to scientific notation. Now, for this last question here, we're going to be using scientific notation and our rules for exponents to answer these questions. So in 2022, the national debt of the US government was about 30.93 trillion. The US population at that time was approximately 332.4 million. So for part A, we want to write the population using standard notation. So we have the population is 332.4 million. So this looks like 332 million and 400,000. Okay. Now we want to write this in standard, or sorry, in scientific notation. So we want to write this in a condensed form. So we're going to take this decimal value and move it 1, 2, like this one, so 1, 2, 3, 4, 5, 6, 7, 8 units to the left. So this is going to be 3.324 times 10 to the 8th power. And we will take all of these values, even if there were zeros. Let's say there were zeros between this 3 and this 4. If we had 3.004, we would take this entire number. We only stop when we have only zeros left over. So this is going to be 3.324 times 10 to the 8th power. Now for part B, we want to write the amount of national debt using scientific notation. So the amount of our national debt is 30.93 trillion. So this is a very large number. This is going to be 30 trillion, 930 billion. And then we just got a bunch of zeros here. Let's see. So this is 30.93 trillion, and we want to write this in scientific notation. So we're going to take this decimal value and move it over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 times. So the national debt written in scientific notation is going to be 3.093. Like I said, we're going to take all of these numerical values here and only stop when we only have zeros left over. And we moved this decimal 13 units to the left. So in scientific notation, 30.93 trillion is given as this here. Now, lastly, we want to use these answers for parts A and B and calculate how much debt this is per American. I want to write this amount in standard notation to the nearest dollar. So we're going to take this entire debt and divide it by the amount of people. This will give us an average on how much debt this is per American. So we're going to take this debt here and divide by our population. Our population in scientific notation was given as this. So from here, we can plug this into our calculator just looking at our numerical values. If we take 3.093 divided by 3.324, this is going to give us, and we're rounding this is going to give us approximately 0.93051. So this is just going to be our numerical value here. Now, for these guys, for these exponential expressions, what we're going to do is use our quotient rule. If we have the same base raised to these two powers in a quotient, what we're going to do is subtract these exponents. So we have the same base of 10, and this is going to be 10 raised to the 13 minus 8th power. So this is 0.93051 times 10 raised to the 5th power. And then lastly, we want to write this in standard notation. So we're going to move this decimal 1, 2, 3, 4, 5 units to the right. This is going to give us $93,051 per American. So this is going to be the national debt per American in 2022. So this is how we would use scientific notation and our rules for exponents in order to simplify these types of calculations. All right, so that'll be it for this video.